Thank you. Everyone, I'm assuming everyone can hear me right now, so
Yes.
hopefully that's the case. So thank you very much for the organizers for giving me this opportunity to speak here. So this work actually started back in Australia, and since I'm looking at things from the other side of the world, even though this conference is about looking at combinatorics and arithmetic and applying it to physics, I'm going to take the other approach of saying, well, I'm going to take physics and apply it to some combinatorics. So this is joint work with Shinsuke Iwao and Kohei Motegi. It's going to focus on these things called Grothendieck polynomials that arose from Schubert calculus, and it's going to we're going to prove some identities with them by using the free-fermion formalism. So to start with, I'm going to just look at a Clifford algebra, and well, the people I know who are physicists will say a Clifford algebra, we have some creation operators, which I'll call psi, and some annihilation operators that I'll call psi star. And they're going to satisfy the canonical anti-commutator relations. So I'm going to have that the psi's anti-commute with each other, the psi stars anti-commute with each other, and the psi and the psi stars almost anti-commute with each other unless I is equal to j. In which case, I get this extra little term, and that's what gives me the Clifford algebra part. And if I just have I and j running from 1 to n, this will be finite rank, and they act on the exterior algebra of c to the n. And how we want to think about this in terms of a more physical approach is the psi i's create a particle at site I, and the annihilation operators destroy a particle at site I. And so this is the spinor representation of the Clifford algebra. So I have an arbitrary wedge, an arbitrary wedge product V. Let's just say it's a standard wedge of things. And I just take that wedge with VI. That's how psi I acts. And then it shuffles it along. And then psi I says, okay, if there's a VI somewhere in this, let's take it as just a simple wedge product, then it removes that the VI from there. And of course, if that VI is not present, then it acts by 0. And so this is in fact, this is the only simple representation of the Clifford algebra. And this gives us a physical intuition. And now we want to take the limit as n goes to infinity. And we're going to just do it in a little bit of care because, we have infinite wedges. And so we need some kind of regularity condition at the end. But with this regularity condition imposed, this becomes what's known as fermionic Fock space. So this regularity condition that I'm going to have is that, I'm going to have an infinite wedge, and I will put them in decreasing order. And if my regularity condition says that if I go sufficiently far out, then all of my jth value is equal to negative j. So this is my regularity condition. This is fermionic Fock space. And basically, I'm going to build a bijection with partitions, assuming a certain kind of balance condition. But I'll get to that in a second. But basically, up to where, and this balance condition basically is wherever I put the point of my partition here. But if I take, say, the partition 4, 2, 1, then if I draw this in Russian notation, every time I have a down step, I put a particle, and I have an infinite trailing of these down steps here. And that's, if I just draw them as particles on a line, that corresponds to my regularity condition that, well, eventually it looks flat over here. And then, well, in this particular case, I've not said what VI1 is, but it would be V1, 2, 3. VI2 would be 0. VI3 would be -2. VI4 would be -4, etc. So this is kind of a very classical bijection. And this is also called the Maya diagram sometimes. And so I'm going to have a special vacuum vector that's all denoted by 0. And that's just, well, all of my particles are going to be stepped just over in this part here. So there'll be a -1, -2, -3, -4, etc. And if you like probability theory, and if you like TASEP, this would be equivalent of the step initial condition. And I'm going to need these shifted vacuum vectors where I just either add or delete particles, but I still have my regularity condition up to a shift. And basically that's amounts to choosing where the origin is. And so formally, here's a formal definition, but we're primarily going to look at what happens when things are balanced, because we don't really, the shift is not so important fundamentally. And so if I create L particles starting from, well, removing L particles, it just kind of clumped together, then I've had a net change of 0 particles, and I get this bijection that I have up here. And this is well defined in the sense that, well, if I add zeros to the partition, that means I'm changing this value L that we see up here, but it doesn't change the actual vector in our fermionic box space. So we have this set of vectors, and they have this kind of balance condition that I'll talk about a little bit more. But so that gives us a nice basis of, well, a subset of all Fock base, but I really want to look at this balance set, which if you've seen this before, this would be the charge 0 component. But, well, being a Clifford algebra, and in particular, the Clifford algebra that we're working with, there's a nice anti-automorphism that swaps psi I with psi I star, which I will very cleverly denote by star. And this is going to give us a dual space, and it precisely corresponds to taking duals in the usual way. So again, I very cleverly am writing this by star. And so we have a natural pairing. And this pairing also works out even better because any operator built up from the Clifford algebra I want to stick in the middle is well defined. I don't need to write parentheses here or parentheses here. So that's good. I can write things like this. And, well, okay, stick stuff in the middle, but I want something where I have a nice basis. Well, I have a nice basis indexed by partitions. And it turns out that this is actually a orthonormal basis with respect to this bilinear product. And the dual vector is just, well, apply star to this. So star changes the ket to a bra, and then I just put stars here and reverse the order because it's an anti-automorphism. So this is a perfectly nice representation of an infinite rank Clifford algebra. But because we're indexing everything by partitions and looking at this subset of vectors, well, it also carries a action of the universal enveloping algebra of GL infinity. And inside of that, there's actually a infinite dimensional or infinite rank Heisenberg Lie algebra inside of it. And the fact that this action also exists on this same representation is known as the boson-fermion correspondence. And we can make this very explicit by introducing these things called current operators, which is now an infinite sum. And then I have this question. No. Okay. So, and then I have this normal product here, which for the most part doesn't actually matter. It only matters when k is equal to 0 in order to make sure that things make sense. I'm just going to brush it under the rug because it's not important for what I'm going to talk about. But these generate the infinite dimensional Heisenberg algebra because they satisfy the relations of a Heisenberg algebra, which is written here. So if I take AM with AK, they generally commute with each other unless M is equal to the negative of K. And then I get a scalar, and this is my center element. And so using this, I can now build half vertex operators, which is just the exponential of this Hamiltonian here. So it has a not too bad definition, but it's still an infinite sum. So I take power sum symmetric functions, but I'm going to have two sets of variables. One is going to have a positive, and that's going to be in the numerator. And then in the denominator, they're going to have negative powers. So for those of you who are familiar with plethism, I'm taking x minus y. But if not, well, I have things that behave positive and things that behave in kind of a dual negative sort of sense. And then I'm just going to divide by n and multiply by a current operator. And then I'm going to take the exponential in the usual formal power series Taylor expansion of these Hamiltonians. And I get a huge, massive sum, but things are actually still well enough behaved that we can actually do some computations with them. So, okay, I've introduced a lot of definitions. If you haven't seen this before, it seems like a lot, but we can describe everything in terms of how the particles move. Well, at least for the current operators. So if I take an AK, what this is doing is it's trying to move a particle k steps to the right, and it's doing it in all possible ways. And again, A0 is special. It just measures how balanced the number of holes and particles are. I can make this precise, but we're not going to use it, so I'm just going to skip over it. And with a little bit of algebra, just looking at this definition here and thinking about how the star works and the anti-involution part of it, you can see that the star applied to AK gives me A minus K, which then allows me to define a star version of the Hamiltonian. And that allows me to define a star version of the half vertex operator. And if I kind of put these two half vertex operators together, I can get a whole vertex operator, but we're not going to be working with that so much. Instead, we will be wanting to see how these act on individual vectors. And so the A minus K acts on the vacuum vector by 0 because it's trying to move stuff to the left, and it can't do that. And therefore the EH star, well, it's just a bunch of negative current operators. They all act by 0 except for the unit that comes from the exponential. And so it acts as an eigenvector with eigenvalue 1. And similarly, on the other side, we have, just by applying the star, applying the duality, we get these formulas, and, well, just the normal ordered product is done so that the shifted vacuum vectors act by eigenvectors, basically, with eigenvalue L. But again, we're not going to be using it. That's just for completeness. The kind of important bit is actually about how the half vertex operators commute with each other. And when we commute them past each other, we get this supersymmetric Cauchy product. So if I basically got rid of this numerator term here, this would be the usual Cauchy product. And if I got rid of the denominator, this is the dual Cauchy product. So this will be useful because we're going to build Cauchy identities later on. Then the next thing we want to know is how the half vertex operators interact with the psi and the psi star. And then from these operations applying star, I can get every other type of commutation relation I want. We end up with an infinite sum when we try and commute them past each other. So if I multiply both sides by e to the h x over y on the right, that gets me my commutation relation, but I get this infinite sum using the supersymmetric homogeneous symmetric functions. So that's written out here, and it's an alternating sum kind of interpolating between the homogeneous symmetric functions and the elementary symmetric functions. And so we just can look at this here, and we see that one of them acts by shifting stuff smaller, and the other acts by shifting stuff larger. And every time we do a shift, we pick up one of these supersymmetric homogeneous symmetric functions. So that's a whole bunch of notation, and we're going to use it to more or less solve an easy problem. We want to evaluate something like this and get something hopefully very nice. And the answer is, well, we actually can do that because we can use this very handy tool called Wick's theorem. Basically, it just comes from doing these kind of local commutation relations between using the canonical anti-commutation relations and realizing, oh, it's a determinant in disguise. And that's the kind of long-winded version. The short version is, well, if we want to evaluate this, we can reduce it down to evaluating a determinant where we just have a single psi star paired with psi I, and then our half vertex operator stuck in the middle. And so to compute one of these terms here, we just use our commutation relation defined that we have up here to move this past the other side. And then we absorb it into the left like this. And that leaves us with this formula here. And then the only way that this actually pairs up is if the index down here equals this index, which then tells us exactly what the value of m should be. It should be this value minus this value. And we get this here. So we have a determinant of these supersymmetric homogeneous symmetric functions. And, well, we know from combinatorial stuff that there's this Jacobi-Trudi formula. And, well, this determinant of homogeneous symmetric functions by the Jacobi-Trudi formula tells us that it is a supersymmetric Schur function. So classical algebraic combinatorics says that when the y variables, there are no y variables, then this is the usual Schur function. And if we take the Jacobi-Trudi formula as a definition of the Schur functions, that gives us this identity. And to get the supersymmetric version, again, plethism, two different alphabets, but that, we kind of get that for free, but we can also kind of see it from this formalism here. So we've almost gone through our backgrounds, but I said there's some geometry running around. So now I need to actually briefly introduce what Schubert calculus is, at least in a small example or one particular example. So the Schur functions, I'm getting rid of the y variables here. They actually are going to have a geometric connection for us. And what I'm going to do is I'm going to take the subgroup of upper triangular invertible matrices, and everything I'm going to do is over the complex numbers. So I'm looking at the general linear group over the complex numbers and by n invertible matrices. And then I'm also going to take a parabolic subgroup. So these are block upper triangular matrices where the upper block will be k by k, and the lower block will be n minus k by n minus k. And again, I'm going to require that those are invertible because I want a group. And I'm going to build the Grassmannian. So the kind of classical definition of this is k-dimensional subspaces of n-dimensional space. But I can realize it as the general linear group modulo this parabolic subgroup. And how we can see that is by the orbit stabilizer theorem. The k by k block fixes the k-dimensional subspace. The n minus k by n minus k block fixes everything else. And then we have the skew terms, but the skew terms or whatever. And hence we get this equality. And why have I made this more complicated? Well, because it now has a group coset structure. Well, it's a quotient, group quotient, but it's not by a normal subgroup, so it's just cosets. But we can now talk about how the upper triangular matrices act on these cosets. And that gives us a nice action. So we can break that up into orbits, and there's finitely many orbits. And these are the open Schubert cells, and we just take their closures. And these are the Schubert varieties. So these are reasonably nice algebraic varieties in general, but and in particular, they basically give a CW decomposition because the B orbits are just look like affine space, and the closures just kind of add smaller little boundary parts. And there's a nice characterization of containment by containment of partitions, because each of these B orbits are indexed by partitions that fit inside of a K by n minus K rectangle. And using this, well, this gives us basically a basis for the cohomology ring of the Grassmannian. And well, doing computations with algebraic varieties and intersections and that kind of stuff is a bit of a pain. So we want to do something where we can just manipulate polynomials. And for this basis of the cohomology ring, we can equate the Schubert variety indexed by lambda, well, it's cohomology class, with a Schur function corresponding to the same partition. And the multiplication in the cohomology ring precisely corresponds to multiplication of Schur functions up to some ideal. In this case, it's, well, we just are quotienting by Schur functions that don't lie inside the rectangle. And so we understand the cohomology ring fairly well, but it doesn't contain necessarily all of the information. We actually lose a lot of information. So we want to make this a bit richer. And so we move from the cohomology ring to the K-theory ring. And we want polynomial representatives. And we know what these are. These are these things called symmetric Grothendieck polynomials. Typically, I'm going to drop the word symmetric because I'm not going to deal with the non-symmetric forms, which come from the flag variety. But so I have these Grothendieck polynomials. And they're symmetric functions. So I can do all of my symmetric function things on them, like apply the omega involution that sends S lambda to S lambda prime, the conjugate shape. But it turns out that for Grothendieck polynomials, we get a different basis, which we'll call the weak Grothendieck polynomials. And both of these bases have dual bases. And in 2017, Liu and Yeliussizov said, okay, I have an involution. I have a basis. Can I do something that is invariant under this basis and basically combine these two together? And not the Grothendieck's with their weak basis, and same for the dual Grothendieck's with the dual weak Grothendieck's. And he introduced this new basis called the canonical Grothendieck functions. And they are not nearly as well behaved as the usual Grothendieck polynomials. The combinatorics involved are a little bit more intricate, but they still actually seem to be a fairly nice basis. Now, this parameter beta here, I've not said where it comes from, but it's right now it's going to be a single parameter because I actually want to take the connective K-theory, and it's the beta parameter from that. But it's telling us something about how far the the Grothendieck polynomial is from a Schur function, basically. I'm not going to get into the details of the combinatorics because I'm going to be doing everything basically algebraically. And like the Schur functions, I'm going to be kind of starting with the Jacobi-Trudi definition. So, I'm light on details here, I know. Now, Galashin, Grinberg, and Liu gave us a way to refine this parameter beta. And, well, I shouldn't speak for Dari since he's floating around here, but at least one of the reasons, as I see it, why we want to refine this is because we want to keep track of where the failures of the, in this, they were focusing on the dual Grothendieck's, where the failure from being a semi-standard Young tableau happens with the combinatorics. And it turns out this actually still expands nicely in terms of the Schur functions. And it doesn't seem to have a geometric meaning as far as I'm aware, but it has a nice combinatorial meaning and in some sense a nice representation theoretic meaning because we still have Schur positivity. But I'm not here to talk about crystals. So let's get to the canonical Grothendieck's, because we want to take these two ideas of refining parameters and combining the Grothendieck with its weak basis together. And that's what Jung-Soo Kim and a bunch of his postdocs and students did in this paper from last year, where they looked at the canonical Grothendieck polynomials, fully refined the two parameters. So I have a parameter alpha that is telling me something about the weak basis, and a parameter beta that's telling me about the normal basis. And we'll just take as a definition this Jacobi-Trudi formula for the big G's. So I have my alpha and my beta. These are alpha 1, alpha 2 sequence of parameters, and same for beta. And I have this supersymmetric homogeneous symmetric function, but I have this double slash where it's not the same as the single slash. It's very different. It's now a product of homogeneous symmetric functions where the difference of the two indices is a fixed constant. And so when m is negative, this isn't necessarily zero as well. So it's very, very big in some sense. And then I have these capital alphas with these intervals down here. And so for any particular set, I'm just going to write shorthand for the I1 variable up to the IM variable. And these are intervals in the usual sort of sense of just taking integer points. So like here, this is everything strictly greater than uj and weakly less than lambda I, all such alphas. And then I have this extra normalizing constant out here that also involves my x variables. And then for the little g lambdas, it's actually much easier because I just take a very big alphabet, but otherwise they're just homogeneous symmetric functions. So they're fairly complicated looking determinants, but not so horrible that all of the kind of symmetric functions and combinatorial data is really lost. So they should be still amenable to study. And what Iwao, Motegi, and I wanted to do was we wanted to see if we can write the canonical Grothendieck using this free-fermion formalism. Because if we can do that, we can actually derive quite a number of consequences from it, basically for free, because of the known relations on vertex operators and half vertex operators, along with their starred versions. And we were able to do that by building upon previous work of Iwao for the non-refined case for when, say, alpha was 0. And what we did is we just modified the psi i's. So for the Schur function, if I get rid of these terms here, in particular, if I set all of the alphas and betas to be 0, this is precisely the same kets that I had before. It's that same vector for the Schur function I had before. But now each psi I just gets conjugated by one of these dual half vertex operators in this way. And similarly, for the little g lambdas, I do that same sort of conjugation by the half vertex operators. And then this bra here is the dual, just applying star to this vector, this ket. So upper indices go to lower indices for taking duals, for applying star. I have this capital BI here, and that's just going to be shorthand for the interval from 1 to I, inclusive, just because otherwise it would make the formulas even worse than what's visible here. And then I also need this extra kind of funny bra over here, where it looks close to the dual of this, except this -1 has vanished, and then basically I'm getting rid of this -1 here and getting rid of the -1 up here. And well, our proof is basically the same thing that we just did for the Schur function. And we apply Wick's theorem and use these Jacobi Trudi formulas to say, oh yeah, Wick's theorem says this is the same as this. Any questions so far?
Could you turn on your camera?
No, I can't. It's because I'm running on my tablet here, so.
I have a question.
Any other questions?
Yes. Hanson, I would like to ask you whether you can extend your formalism, which you use for the operator, which you call the current operator, which is effectively particle whole creation, to another operator, which would include two fermions, like a pair of fermions characterized well in the BCS theory of superconductivity.
I'm not sure about that. I don't immediately know. Sorry. Any other questions? All right. So now that we have these vectors, we want to know about their orthogonality. And it turns out that these vectors are orthonormal as well. And we get another orthonormal basis for fermionic Fock space for these, even with these additional parameters. And this is actually one of the main theorems and more powerful, basically the biggest result that we're able to use, because that allows us to prove branching rules. And how we do that is we just insert an identity operator that, well, takes sums over lambda, and oh yeah, I did include it here. So we just use an identity operator like this because it's an we have an orthonormal basis. So if I pair with lambda and then well, and that gives me my coefficient of lambda, then, you know, orthonormality, linear algebra. And so armed with this, we get refined versions of the branching rule formulas for canonical Grothendieck's that Yeliussizov had, as well as fully canonical versions of results that Book had. And we need this extra double slash version that Book used to relate it to the coproduct, or I mean, it's related to the coproduct in symmetric functions. And it's the natural thing that appears in the branching rule, because I'm not using that kind of double version of the bra, but the dual version to the lower ket. And so we get these additional functions that, as far as didn't appear in Hwang at all. And so we're able to get Jacobi Trudi formula, as well as we also have dual Jacobi Trudi formulas as well. But I'm not going to write those out here. And as another consequence, by looking at how the kind of double bracket bras decompose into the singles, we can explicitly relate the single slash with the double slash. And basically we remove inner corners, but at the cost of doing an alpha plus beta corresponding to the index of that corner. And this is a refinement of what Book had as what, and a canonical version. We also get a new proof of an identity in Hwang et al. That says if I apply the omega involution to a refined canonical Grothendieck polynomial, it acts as you would expect on the partitions. It sends them to their conjugates, and then it interchanges the two parameters because we built it up thinking of it as the combining the Grothendieck's with their weak basis. The alpha was the weak, the beta was the regular, and well, the weak was defined by omega, so we should basically swap them. And then the same thing for the dual case as well. And for our proof, we needed to use a slightly different version of the vectors that naturally encode the how conjugation works at the level of the Maya diagrams. But just due to time constraints, I'm not going to go into that. But we do get a new proof of this. Then we can also use this formalism to insert identity operators for the usual Schur functions, where we just use the original bras and kets that we had before. And that then gives us the decomposition of all of our Grothendieck's and canonical Grothendieck's and their duals in terms of Schur functions. In the dual case, we recover the formulas of Hwang et al. But in the regular case, well, for the single slash, we actually get a slightly different determinant formula than they have. And then we also have new formulas for the double slash. And so this is basically a trivial consequence, again, by just inserting an identity operator. Hwang et al. Used this Schur decomposition to note this as a consequence. And their proof was combinatorial, Plethys, as well as algebraic, kind of doing a lot of manipulations that way. So it our proof gives a very slick using this free-fermionic formalism, but very different approaches. And then we also get different forms of skew Cauchy identities. Well, these are all basically consequences of the first one by applying the omega involution on the x's or the y's, but we can also just prove them directly using the half vertex operators. And it's just evaluating this half vertex operator or evaluating this vertex operator in two different ways. One, we insert the identity element in here, and then two, we do the commutation and then insert the identity element. So it just becomes a very simple computation. We can also prove Gambelli type formulas or determinant formulas involving single rows of the Grothendieck's, but well, we actually use with alphas 0. We get these skew Pieri formulas, which they don't automatically look like actual Pieri formulas, but if you specialize variables appropriately, you can recover Pieri formulas from them. And I can also get kind of dual formulas by interchanging the G lambda mod mu, the little g's with the big G's, but I have to use the double slash. And again, this is using a formula similar to this, but we have 3 half vertex operators inside instead of 2. But it's still just a simple kind of consequence of using the formalism that we've built up. And we can also answer a problem of Yeliussizov about where he was asking about how the expansion of the canonical Grothendieck's behaved when we expand it in terms of when alpha was 0. And this was some kind of Kasdan-Lustig type properties that he was asking about. But it turns out that this is actually just completely false. And by using our formalism, well, we have, of course, orthonormal basis when alpha is 0. And so we just insert these other kinds of identity operators. We get some determinants, and then we can look at what Hwang et al. Have and get combinatorial data from that. And using this combinatorial data, we were able to find some explicit examples just by direct computation. So that's what we've been able to do with this. What can we use this for? And what kind of is the next in our, after this is, well, Iwao in his papers on free fermions with canonical Grothendieck's had these Schur operators that they add boxes to the partition if possible, and basically can grow out the partition, and writes them in terms of operators acting on the Fock space. But in his case, he originally just did it for all the beta parameters equal to a single value, and alpha is 0. We've been able to extend them for the canonical Grothendieck's for alpha and beta being fully refined, as well as the dual case, but we need one of the sets of parameters to be 0. For the generic case, it actually seems to be kind of hard because you get infinite sums that don't behave so nicely. It doesn't seem to satisfy, we can't find combinatorial descriptions for that satisfy the Fomin-Green non-commutative symmetric functions, the Knuth relations. Right, they don't satisfy the Knuth relations, it seems, or at least we haven't been able to find them. And why, and with the Schur operators, as well as the Jacobi-Trudi formulas, we're able to make a connection with a version of TASEP, so the totally asymmetric simple exclusion process of particles hopping on a line, where the weights of the particles and the interactions of the particles, this is a discrete TASEP, to be precise, because I need to have update rules, and there's pushing and blocking behavior. And the Schur operators basically encode the local particle dynamics. And the formulas that Decker and Warren had are basically exactly our Jacobi-Trudi formulas, specialized with all of the X parameters to be 1. But yeah, we'll I need another paper to be able to talk about that. And then we'll also give a direct combinatorial proof of the Hwang et al. By branching down to a single variable. And at that point, then we have some analysis to do using the Schur operators, actually. So, well, I shouldn't quite say that, but the underlying vector and vector analysis ends up being this very similar. So anyways, that's all I wanted to talk about. Thank you very much.
Thank you. Are there questions? Oh, I have a question. So in our paper with Fomin and Grigoriev, so we computed Schur functions, Schur functions, and so other functions using cluster technique. So we have to specify initial function on the initial seed, and then we just apply some sequence of cluster mutations, and then the corresponding cluster variable becomes a Schur function or Schur function or super Schur function. And this reason is just because of this Jacobi-Trudi properties. It's Jacobi-Trudi because if you have determinant, then you have Plücke relation, and Plücke relation is a kind of special cluster mutation at the covalent vertex. So, and because you have also this kind of Jacobi-Trudi, so therefore it could be that you have to specify at the initial seed just special values of your functions, and then you can compute all other. So, and therefore, in some sense, it could be give a hint that there is some universal property which just so handled by the same cluster combinatorics, but only you have just to change your initial seeds, just specify a special function just to put functions. Maybe it could be somehow seen in use, or maybe the branching rule would be just could be seen from this technique or something like this. So I think that maybe it works because then you have a theorem, then you have just the symmetry. So then you have lambda mu and with alpha beta, and then you go to lambda to conjugate partition and with alpha and beta switch. So I think it's could be seen maybe from this.
Yeah, because that would be nice if you can see the this statement very easily, because we actually had to like so proving this is
which we might guess just to apply this cluster technique just to understand this.
Yeah, because this is not so easy, because we needed to find what those conjugate vectors actually are, and the Hwang et al. Proof, it goes through the Schur function, but it's not very satisfying in some ways. Like there's no direct, really fundamentally direct proof of this, and I'd be interested. Like maybe does this also work for? Do you know if you get Lascaux's multi-Schur functions?
You mean double?
Yeah, well, not double. Lascaux has this like generalization of Jacobi Trudi, where basically you're doing kind of arbitrary alphabets at every point in the Jacobi Trudi formula, and if you choose this appropriately, you can recover the dual Grothendieck, dual canonical Grothendiecks. This was mentioned in Iwao's recent, or in the one of his like his 21 paper. So but we should talk more on that.
Are the multi-Schurs positive in any way?
Maybe in special cases, but I don't know in general. In this case, we're using alternating in alpha and beta. So like the positive version would be negative beta, negative alpha for the big G's. We're taking the little g's to be positive sums. So we're not even technically positive for the big G's, but yeah, since the little G's are positive in multi-Schurs, at least in this special case, they are, but I don't know in general.
I'm asking because usually the cluster mutation approach doesn't give you minus signs.
I don't remember. It's quite possible that they're positive, assuming you're passing positive parameters.
It would be a Laurent polynomial, which is was positive, but then you have division that it could be, so it's not obvious that it would be. Using cluster, you will have short positive, but however, I guess that it has to be. It's not directly from cluster theory. But for Schur function, yes, I think that we prove that any cluster, so if you just make the specialization of cluster variable, which allow to obtain Schur function, then you can look for other cluster variables. So then they are some polynomials, and then they are Schur positive. Okay. So we are a little bit delayed, so we have start the next. So thank you.